Okay, welcome everybody. This is a catch-up lesson for the folks that are at IASA Season 3. Hope the tournament's going well, and hope you guys are having a good time. Today what we're going to do is talk about the Heisenburg uncertainty principle. And I give this a shot, try and include as many of the things that we did in class, but I really want to encourage you, if there's things you don't understand, make sure you find some time, come in, and we'll get things straightened out. So first thing I would suggest is hit pause and print the notes that I sent you based on this lesson so you can follow along and make any additions you need to make, okay? So the Heisenburg uncertainty principle is based on position and momentum and the uncertainty of those two things. As the uncertainty of your position decreases, so you become more and more certain of where a particle is, you are less and less certain of the momentum of that particle, that is the velocity, both speed and direction of it. Okay? So in this picture here, this is in your notes, you'll see there's a picture of a tennis ball right here in midair. And so what I would ask you is, where is the tennis ball? And with very, very low uncertainty, you could tell me, well, it's right there, Davis. Okay, so your uncertainty of your position is very, very low. Now I'm going to ask you, okay, tell me about the momentum of the tennis ball. That is, tell me how fast that ball is going and in what direction. And that becomes a lot tougher with a photograph. This ball could be moving left, right, up, down. It could be going fast, slow. It might not be moving at all. It might be at the highest point in a vertical climb and completely at rest. And you have no way of knowing. And the reason you have no way of knowing is because your position is so certain that it has impeded your ability to measure momentum. Okay? The contrast of that is, if I see this video, hopefully it pops up soon. Oh, I do not want rainbow balls with a 15-minute. It's too slow. Okay. All right. There we go. All right. So what I'm going to show you now in the next 25 seconds is the fastest tennis serve ever. And so as he lines it up, I'm going to mute it. Okay, so he serves it up, and I'm going to ask you, where's the ball? And that's an impossible question to answer. And the reason is because the ball is going too fast. It's going 263 kilometers an hour. If I ask you, where's the ball, by the time you point to a spot, the ball is gone. So you can't tell me very much about the position. It's relatively uncertain where that ball is. However, if I play it again, and I ask you about the momentum of the ball, you'll tell me that, okay, well, the velocity is 263 kilometers an hour and it's going in that given direction. So you can tell me about the momentum with very, very little, very, very low uncertainty, but the position is very, very hard to ascertain. Okay? So that brings us to this. This is the equation for the Heisenburg uncertainty principle. Delta x is your uncertainty of your position, your plus minus of your position, and delta p is your uncertainty of your momentum. Okay, and if you multiply those two together, they have an inverse relationship. That product is going to be greater than or equal to this number. Now this is a very small number. It's a very small number because Planck's constant, h, is 6.6 times 10 to the negative 34. And then we're going to take it and make it even smaller by dividing it by 4 pi. So as you can see, the product of these two is, I mean, it could be greater than that number, but it can never be smaller than that number. And what that does, that has huge consequences in terms of energy. I'm just going to walk you through the derivation of momentum and position with regards to energy. Let's do it nice and slow here. So here's our initial equation. The uncertainty of momentum times the uncertainty of position equals h divided by 4 pi. Okay, so I take that initial equation and I'm going to do something probably unexpected to it. I'm going to multiply the left side of the equation by delta t over delta t. Now, it's the same number, so I'm multiplying it by 1. It shouldn't change anything. But then what I'm going to do is group this delta x and these two delta t's. Okay. When I get that, I get the original delta t on the top times m times, now this is delta x over delta t squared. And then finish off the equation, times delta x equals h over 4 pi. All right. Mass times a change in distance over a change in time squared. Well, change in distance divided by change in time squared, that's an acceleration. And if you take an acceleration and you multiply it by a mass, you get a force. And so this boxed in equation right here becomes force. So you have delta t times F, force, times uncertainty of position equals h over 4 pi. Almost there. We're almost done. Force times delta x. Okay, a force times an uncertainty of displacement or uncertainty of position, that's work. And so delta t times work, or a change in energy, equals h over 4 pi. And so what we've done is we've started with this initial Heisenburg uncertainty principle, and we built a new equation involving energy and time. What this means is that we can create energy that wasn't there before for a limited period of time, delta t. The more energy we create, the less time we're allowed to have it. And it's based on this left-hand side of the equation, h divided by 4 pi. All right, so 2 sample problems. Trim was good enough to help us out with this first one. We're going to show that this doesn't really apply. You can't have a person suddenly gain energy, and he used the example of going up to see Mr. Venables up on the 3rd floor. And so if he were to instantly teleport up 1 floor from the 2nd floor to the 3rd floor, that would be a height increase of 3 meters. So we asked, well, can he do it? Well, Trim is 80 kilograms. He's got to go up 3 meters against gravity, so he needs to gain a delta E of 2,400 joules. We'll throw that in the Heisenburg uncertainty principle, and we get that he is allowed to have that gain of 2,400 joules for only 2 times 10 to the negative 38 seconds. Okay, now that is an unbelievably small amount of time. So small, in fact, that if we actually consider it and say, well, he needs to travel 3 meters in that amount of time, he has to go 1.38 times 10 to the 38 meters per second. It's not going to happen because that's much, much greater than the speed of light. And so therefore, sorry Trim, you're out of luck. You'll have to take the stairs. You cannot instantly create the energy to go up to the 3rd floor. But it's different for an electron, because an electron is a lot smaller than Trim. Okay, if you have an electron and an electron wants to gain 1 electron volt, or this is in your formula book, 1 electron volt equals 1.6 times 10 to the negative 19 joules. So if we put those same numbers in, the electron gains 1.6 times 10 to the negative 19 joules, we find that it can have that energy for 10 to the negative 16, 3 times 10 to the negative 16 seconds, which again is a very, very small amount of time. How far can the electron go in that time? Well, if it travels the speed of light, which electrons do travel close to the speed of light, and you multiply that speed of light times this time, you'll find that the electron, the maximum distance it'll travel is 9.84 times 10 to the negative 8 meters, which is still inside an atom. It's a reasonable distance for an electron, which is why electrons are known as electron clouds sometimes, is because you'll get a situation where the electron is here and then instantly over here without having traveled across. Okay? All right, so last thing today. What this done, this created energy delta E can only exist for a finite period of time, delta T, before it is absorbed by the original particle. Okay? Virtual particles or exchange particles, that's this created delta E. They're created from E equals mc squared. Okay? And so a particle creates an energy delta E. That energy is used to create a virtual particle with mass m, which then goes out and is allowed to exist for a small period of time. If during that small period of time, the virtual particle is absorbed by another particle. Well, now you've just created force, okay? Because you've had one particle has created energy and then lost it to another, and so they've essentially applied a force on each other and potentially changed the direction of each particle. And that's where the four fundamental forces, that's how they exist, is through the Heisenberg uncertainty principle. Okay? We're going to pick it up next class. We're going to talk about range and Feynman diagrams. And I have another screencast which I asked this last year that hopefully will help you with that. So hope you guys have had a great trip. Hope things are going well, and we'll talk to you soon. Take care.